And once again, we're looking at a projectile motion problem. For this problem, we're looking for the angle theta at which the object that he's throwing goes out, comes right back in, and lands where it begins. I kind of see this as if you're starting an Ultimate Frisbee game and you go and you throw a really, really great start, and then it goes straight up in the air and comes right back to you. And because of that, there is a force of drag and a force of gravity on it. And just like we did before in the first projectile motion problem, we're going to draw a free body diagram. And this has gravity and drag, the force of drag. And because of the existence of acceleration, it is implied that the sum of the forces does not equal 0. But you can also look at the free body diagram and see that it is extremely imbalanced, so you are going to have an acceleration there. And what that acceleration looks like is force of d plus gravity equals mass times acceleration. I'm actually going to define this on the outside, so we'll have a negative g there. And then you get an acceleration that is a function of these forces. And they've given us the values of acceleration, so we don't have to find them from the forces, but I wanted to solve for the forces in that way so you kind of get an idea of what it would look like if you were doing a full dynamics problem. And negative g. So we get a nice acceleration formula there. This is different than the acceleration that we looked at with the first problem, because the first problem only had gravity. In this case, we have the x force, x acceleration as well. And because of that, the derived equations in the x direction are going to be a little bit different, so let's go ahead and start by deriving those. And I'm going to do this a little bit more simple than what I did last time. I went into very detail last time. But here, we're just going to quickly do the derivation. And so we see that when you take the integral dx dt, you have this function here. Before, our x, or our v, was just a function of v. And this was not in the final. However, now we have the velocity that is a function of t. And that's going to help us a lot in this equation, or this problem, because these are not helpful at all. They don't do much for us in finding the solution, because if we were to use the position equations, they would all just be equal to 0. Not very helpful at all. Well, I guess because they're squared. Still, it's not very helpful because it doesn't give us the information that we need. So where do we go from here? From the problem before, we derived v of y with respect to t, and we just found v of x with respect to t. And we have acceleration, which is where we got these equations from, so we don't have to look for that in the problem. But we have v naught, and we have an intermediate time. So if you're looking for theta, that's nice, but when you have these two values, you can use them in terms of each other like we've done before. So this t is going to be a connector of these equations. And we did a substitution looking for the range, and we did a substitution looking for v with respect to y. But here, we are going to make this equation v of y as a function of v of x. And to do that, you solve for time. So let's go ahead and do that. If you are looking at the Vy of t equation, you'll get that Vy of t equals negative Vy naught minus gt. And this should be positive. Then when you plug in the value that we know, which is 12 cosine theta, and it's cosine because up here is sine, and over here is cosine. So we'll have to use the cosine to find the y value. Equals 12 cosine theta minus 9.81 t final. And when you solve for t final, you get it as a function of theta. Then we'll use the x equation and say set Vx equal to Vx naught minus 0.4 t final. Plug this into the v of x equation, and you'll get 12 sine theta equals 12 sine of theta minus 0.4, and then the value there, 2.45 cosine theta. And solving it, you get a nice tangent function, which is easy to solve for, and you get an angle of 2.33, which is pretty small in terms of the throwing, so it's not going to be a large angle like you would get as if you were throwing a frisbee, so it's probably throwing something like a baseball. But that is another way that you can solve for it and go through all of the equations, is by setting v of y and v of t together and using time as an intermediate function for these two equations. So I've said this before, and I will say it again because it really helped me when I was taking this class. If you don't know what to solve for, start looking to solve for time, because chances are you're going to be using time as an intermediate constant. And if there was a cheat equation or a substitution equation that you've already learned how to derive before, you would have wasted time thinking about that equation, and so if you solve for time, you at least got partially there. So that's just a trick that I use for solving these, but the best way to get good at solving these problems is to work a lot of them, because then you start to understand which equations to use and which ways to go when you're given a certain number of variables and you're working towards a solution.